So yeah, I've been looking at the defense part of this cyber, and also now starting to move to onto the AI now. Oh, yeah. To give you a kind of a practical example of what actually is there and what can happen if you use AI or machine learning in kind of old environments in new ways. So the first talk was doing a nice job of introducing where you can use AI in cybersecurity, and that was more concentrating on using AI as a tool. My viewpoint is more using or what happens if AI itself is a target for attacks. And Lerta will give, I doubt, an excellent talk about the technical details of such attacks. Anyway, when you have machine learning controls in your existing systems, it means that those machine learning controls are also a possible target for attack, and they could be used specifically to evade something or to attack the system in general. Here's a more research-based. This has not been, at least as far as I know, has not been detected live, but researchers are interested in operational technology, or OT, basically industrial control systems security. And there's kind of this secure water treatment plant test board that's very popular to be used in research when you try to demonstrate some practical attacks against OT or industrial control systems. As the first speaker mentioned, the AI or machine learning components are already used as intrusion detection systems. Also, it's a growing trend to use them in industrial control system intrusion detection. And the way they basically use their system is to try to predict what the actual sensors will produce. And if the sensors suddenly start producing values that are different from the prediction, they will raise an alarm. So for example, here is an example, a water level sensor and flow sensor. And included is kind of a machine learning intrusion detection system that forecasts the time series of each of the sensors. And in phase one, we assume that there's an active general cyber attack on this watt, but these sensors themselves are not attacked. So just to give you an idea of what is going on, there's a water treatment plant. So basically it purifies water, and the aim of the cyber attacker is presumably to alter some values, so like salt or other substances to dangerous levels, so that the water will be dangerous to citizens. Some state actors might want to do it, or activists to promote their agenda. So this is considered, at least considered a real threat. Now, here, let's see if you can you see my cursor? So here is the start of the cyber attack, and here's the water level indicator or sensor, end of the cyber attack. So this orange line here is what the sensor actually shows. Basically, there the water level goes up too much. but as the prediction, the black line should be the change in the normal conditions should not be that high, it will raise an alarm. And the same things for the flow indicator. So if the flow indicator drops dramatically below what would be plausible from the machine learning intrusion detection system, that will also raise alarms on the depending on what the actual method of calculation is. However, if there is this general attack on this system, and then we assume that this level indicator sensor is also attacked in such a way that you can control what it outputs, and you make it the output like very precisely targeted for this IDS sensor. In the IDS sensor for the flow level indicator does not see any crucial change, because the IDS sensor is actually fooled to think that this kind of a change in the time series is exactly as predicted. So the IDS will not produce an alarm because it thinks that it doesn't know that this level indicator has been compromised, and the flow level indicator that has not been compromised shows that everything is fine. So no alarm is generated, and this cyber attack will be able to commence. This kind of scenario is an example where you could use you would try to fool the machine learning component, which is used as cybersecurity component, to kind of this an evasion attack. And it has real consequences, because then you are able to continue doing your bad things in the industrial control system realm. Another example is actually an upcoming publication. I noticed that Martti Lehto is on the audience. That's part of his book. So we'll see here. So, here I was charting what applications are in the logistics arena are using machine learning, and there are quite a lot of them actually. So the use of machine learning is spreading very fast. However, there is only a limited number of research in general in these areas, even though there are known incidents on some of them. So this means that yes, there definitely is machine learning used in many real life applications, and there are incidents in those applications. So it's just a matter of time, but before something really bad happens. This, of course, has not gone unnoticed. So there are a lot of authorities out there. I'm talking about information security authorities, which are responsible for giving guidelines, guidance, regulations, standards out there to try to protect the mainly government and critical infrastructure information, but that guidance is also very usable in other areas as well. In Finland, Traficom is the one who's actually doing this work. And the rest of this talk is going to be about the regulation and standardization of cybersecurity of AI. I will take a couple of viewpoints. The first viewpoint is that from ENISA. ENISA is EU Agency for Information Security. I think it's European Network Information Security Agency, what the abbreviation stands for. And they are assuming this kind of a 6 main stage life cycle for AI and also for data, like here. The point is that each life cycle phase, both for system and data, needs special consideration. And this is a iterative feedback model, starting with the business goals and ending with business understanding, which I hope is gained eventually, since there's the AI is such an emerging field. I have the feeling that even if businesses are able to give their business goals and business drivers, then having the business understanding, even if someone else deploys the AI there, as it well trained, tuned, and deployed, still having the understanding will lag behind. Interesting thing is that if you look at the life cycle of an AI system, the planning and data forms the first part. But then if you look at the data lifecycle, it's actually most parts of the data lifecycle actually is happening here in the first phase. It's kind of a natural, but still it seems that the standard is more focusing on selecting and pruning the data, the input and training data, to be sufficiently secure. ENISA, at least this 2020 document, does not explicitly address adversarial training. That is something that's still emerging. Most of the standards or the existing proposals for standards or AI cybersecurity management, they address adversarial attacks as a sidetrack, that these are a threat and they should be handled or addressed, but they do not still go very deep into that. An exception is NIST, where I'm going next. This is the NIST AI lifecycle circle. Okay, I will return to the NIST standard structure later. But however, NIST has this kind of a more modular. It's not a standard. It's a guideline. It's a guideline, and it's more modular in the sense that the main document is keeping. They try to update it, and there are other documents which are more detailed and are updated more frequently. They also have a adversarial kind of a attack glossary and explanation best practices already there, which is now, I think, its initial public draft stage as of October or September. I haven't checked quite recently if it has got a final status. Even this AI 101 got final status this January. Anyway, you can see that comparing to the ENISA standard, this also has 6 main stages, but it is very focused on this TEVV controlling functions. The TEVV stands for testing, evaluation, validation, and verification. So the main idea in the NIST guideline is to have these dimensions and several interdependent actors to stage. And one of those actors is an actor that is performing these TEVV functions. Moving from one main stage to another includes using the TEVV functions to make sure that you are following at least some sort of scrutiny in the security and robustness of the AI. This document does not actually give any obligations. Yeah, let's go to the here first a bit. So what are the AI-specific cybersecurity risks that the NIST has identified. First, there's the large dependency on data, of course. And if you are using very large model, you will need some processing resources. I don't know exactly how much, for example, OpenAI is using computing power to power all these ChatGPTs and DALL-Es, but it's not just 2 or 3 servers. You need quite a lot of them. If you have third-party data, this has already been addressed, how you control and honor your obligations to other data providers. That's kind of difficult to address. There are differences in how to train the AI compared to conventional software development process. SDLC has security controls, especially if you think of like DevSecOps. But these are not applicable in the AI training because it's very much different. Software, you can test the software or the AI as like in conformance, whether it actually does what you were expecting it to do. But on the other hand, we think about cybersecurity, you should also test the software or the AI of some undesirable things that it does not do those that you really don't like it to do, like expose unnecessary credentials or have conditions that enable attackers to enter your system. So these are called side effects, and how to actually test your AI against these is kind of a emerging field yet. Opacity or reproducibility is something, or transparency of AI is something that's very important to security authorities. They really need to know what's happening under the hood before they can put it into the most critical applications. If you're doing scientific work or forensics and you get some idea of the AI system, then how can you be sure that the next answer is going to be similar or sufficiently similar, let's say. From my personal experience, I was trying to create, for example, this picture here from the DALL-E via the ChatGPT interface, and having one image and then requesting small changes to it will likely result in a completely different image, unless you know your prompt engineering, which I'm not very good at the moment. And then this concept drift and data drift, model drifts, which are kind of intrinsic to the AI systems, and these need to be addressed in maintenance functions, which are more frequent than in conventional software engineering. So NIST guidelines are packaged in what they call a risk management framework for artificial intelligence, or AI RMF. Good question would be then, how about ISO 27K? They already have a risk management guideline there. There are lots of risk management documents, guidelines, mandatory documents, regulations there already. So why not? What makes it different? Well, basically, you have to consider there's a bias in data. Generative AI has kind of unknown risks, AI-specific attacks, evasions, poisoning, model stealing, etc. And what this transfer learning concept, if you reuse AI again, then you cannot be, well, the previous speaker was talking about, if you reuse the AI or pre-trained models, then you're not actually sure what can be in there. Then again, we would not like to reinvent the wheel. So the NIST AI RMF is following the basic risk management style. So like senior management commitment, training your personnel, general awareness are basically something that you can copy from any other risk management guideline. So far, the ARMF aims to be voluntary. It doesn't want to pin down any use cases and wants to be used in all sectors. This makes it kind of general, but so far, for example, if you look at industrial control systems, there are cybersecurity standards, sure, but none of them actually address AI or machine learning. That kind of standardization for cybersecurity is still very much emerging. The risk framing approach is more safety style than security style. If you look at this circle, in the heart of it is people and planet. So they are really going to be sector unspecific and considering very large models which could actually technically go rampant like some Skynet. So that's why they already include the safety aspect there and societal implications and risks as well. The TEVV I already mentioned that throughout the life cycle you should have controls in place when you move from one life cycle phase to another. You should do this certain set of tests which are phase specific. How the AI, the NIST RMF is structured. Basically, it has 4 main documents. The AI 101 is the main document, the vocabulary, and the newest one is a taxonomy of adversarial machine learning, which is developing still constantly. This is just the initial public draft, and a playbook that they intend to update also very regularly. So basically, this kind of a core part of the RMF document, and the playbook has kind of a suggested detailed actions. This kind of approach is very common to standards, which are like common to horizontal standards. Horizontal standards don't like to mandate organizations to do specific actions because they are organization specific. Instead, they do give a general framework and then examples of how you could do it if you have absolutely no clue how to manage this kind of risks in your organization. It's a big document. There's some topics here that are AI specific. So the whole idea of the RMF is to have 4 main topics from govern, which is to govern all of the stuff, and then start from mapping to measuring to managing. And the goals of this process is to make the AI to follow the validity, reliability, accountability, transparency. There's a kind of specific terminology used in NIST RMF, what they mean by validity and reliability, and it's the basic requirements. It should be both valid and reliable, and from that you can have additional requirements to make it safe, secure, resilient, etc. But those 2 definitions are the basic ones that need to be fulfilled before you can make it have other nice properties about the AI. The accountability and transparency are kind of like a vertical, but in a vertical direction. So they apply to all of these attributes. To see some of these AI specific function is what is very visible there is the safety and safe decommissioning or deactivation of the AI is a requirement. It's a kind of a basic human reaction if you are doubting that something is very self-determined, can possibly coordinate itself to emergent behavior, then you want to have off switch. The TEVV It's visible throughout all the phases, and also this kind of a risk estimation of AI during deployment or after deployment, that what can it actually do, especially with respect to this emergent behavior. In the management phase, it's good to notice that there are this NIS2 type, which is the European Network Information Security Directive, where you're obliged to report kind of incidents and threats to your customers as well as your supply chain. And this kind of a requirement is included here in the management phase of this RMF. Of course, the whole RMF is voluntary, but if you want to claim compliance, you probably need to implement some reporting functions as well. Okay, going forward to back to the ENISA risk management model. After the life cycle, their model is very basic. If you look at ENISA works and documents, they are very comprehensive. They start from old and tested, from threats to assets to vulnerabilities, and then do mappings between them, that which kind of assets apply, which kind of threats apply to which assets, or produce which kind of vulnerabilities, and at which life cycle part of the AI system. This is just also more than technology. However, the current risk management is kind of divided into two parts in ENISA. There are two documents, one for general AI and another one for pure machine learning. The more general one, it starts with to be in general AI, but then the vulnerabilities are only addressed for machine learning. Technically today, using the word AI and machine learning are kind of interchangeable, because machine learning with artificial neural networks is basically the main trend that the future applications use. Of course, you need to be aware that there are older existing kind of optimization algorithms still in use, which use some other AI than machine learning. But those are kind of a different story. It is a very comprehensive, 72 asset types identified, 96 different threat types, but most of them are not AI intrinsic. They are general to all cybersecurity. So having or extracting AI specific threats and assets from ENISA model can be quite challenging, but then again, it also encourages you to think of the whole thing as a integrated discipline, which is what you should do. So when you start deploying this from scratch, you should take everything in at once. But in order to learn what to guard specifically, it might be a bit difficult to read. This machine learning specific model is basically a known attacks paradigm added with human factor consideration. This uses, many of you who have researched the existing machine learning specific attacks, you can find them there. But based on these different categories, they have also gone a bit deeper to have together 63 vulnerability types grouped under each of these attack types. Okay, It seems that I'm close to end. I have to go a bit further. There's also MITRE. Those of you who MITRE, they publish this kind of attack framework where you can. It's compiled of known cyber attacks, and they have been able to integrate machine learning into this attack framework, which is kind of interesting to see where you can actually have machine learning as part of a general cyber attack, where it is actually important, where it's less important. An interesting thing is that there are already information security authorities are planning on how to do security certification of machine learning. So for that, you need model robustness metrics. So it is currently, there are some ideas to attain kind of exact criteria or that you can attach to exact security levels. And the way to get evidence on products actually meeting the criteria is that you need verification and testing. And there are some methods already there, or proposed methods for adversary models. They're kind of like general metrics, which is like attack success rate, and type-specific metrics like against confidentiality, accuracy of the extracted training data or model parameters from the point of view of the attacker. The integrity attacks has actually progressed a bit further. What you should be measuring, and there are kind of different security models out there, like a distortion of data with bounded attacks and unbounded attacks, where the metric does actually metrics are non-trivial, and choosing the metric also matters. I think I will stop here now because of time constraints. But an example of how you assess machine learning adversary robustness, there are tools already, starting from empirical testing to formal verification. There are already some estimates on the size of the artificial neural networks. What can you do? These numbers are for feed-forward networks or unrolled recurrent networks. The size of the total nodes or the depth of the network, including the input and output layer. So, but however, these methods, they depend on the robustness metric. So when you are doing your security certification or evaluation and showing some other party that my machine learning implementation is this robust against adversarial attacks, you need special care of selecting the metric and selecting the tool and the method. Certification is costly in any case, so that might be a question when you have an actual business case to do the certification. Of course, if you are in the field of providing solutions to authorities, this might be kind of a mandatory requirement rather than a business case. But then again, it's a business choice of the business area. I'll let this one to be what are practical AI cybersecurity research topics out there if someone wants to take more practical topics instead of going very deep into the network theory. Thanks.